Welcome to the second half of PG Day. I'm going to be talking a little bit about Postgres 9.2. I'll talk about the new features. I'm going to do a bunch of live demos, which is lots of fun because you get the opportunity to potentially see me wipe out. So live demos are always more exciting for that reason. And so we have a lot of stuff to cover because there's a lot of features in 9.2. So we're going to go ahead and get started. And if there is time, we will have questions at the end. So, Postgres 9.2. I've been calling Postgres 9.2 sort of our NASCAR release. How many people were watching NASCAR last night? They had it on in the bar. Anybody? Is anybody here a NASCAR fan? We got a couple. Well, we got a NASCAR fan, right? So, what does NASCAR stand for? No, it stands for woo-wee! NASCAR! I learned that in North Carolina. I went to North Carolina for the first time this year. I got my hat, right? So, anyway, I've been calling this kind of the NASCAR release because this is really the fastest Postgres ever. It's really, really fast, even out of the box. And you do a lot of stuff with it. So we're going to actually go through some of the ways that it's faster, some of the ways that there's new features and that sort of thing. I've got a little racetrack set up for us here. So we're going to talk about improvements in read scalability and write performance and index-only scans. These are all performance features here. Cascading replication, which some people are excited about. The new JSON support. We're going to go through the dark and murky tunnel of SPGIST. Talk about range types, one of my favorite features. Some improvements in managing migrations and deployments. Some improved admin tools. Some of the other features. Some of the stuff that's coming in 9.3. And then, if we have time, we will take questions. So, Monaco. Yep. Monaco. Yes, that is. Yep. So, but this is not Monaco. No. So, let's get started. Everybody ready to get started? You ready to start your engines? Okay. So, first of all, read scalability. There's a lot of work. Basically, now we finally got access to some much bigger machines, thanks to HP and the University of California. Got some 64-core machines with a terabyte of RAM to try out Postgres on. We discovered, hey, we're not using all of the resources on the system, and particularly in a case where Postgres should be really, really amazingly fast, which would be a read-mostly database that was little tiny. We weren't anywhere near as fast as we should be. And so Robert Haas and Heike and a couple of other people started working really hard on read scalability and the ability to read, doing a very large number of concurrent reads at once. And they developed a whole bunch of interesting and cryptic sounding patches, things called like fast path sorting and PR-proc shared memory optimization. And what it really, and my personal favorite, keep hot search buffer. And what this really amounted to was eliminating a lot of locks and making a lot of low-level operations looking for data faster or not linear scans, so that they actually had some scalability. And you don't have to understand these individual changes because they work for you automatically. You don't have to do anything. What's actually more important is what the results were. So this green line here is Postgres 9.1. And as you can see, as we had in the past, Postgres 9.1 up to about 20 concurrent processes continues to scale up with each additional workload that you add to it. And this is on a 64-core machine. But at about 20 concurrent ones, it flattens out. And you stop getting additional throughput by adding more concurrency. So in 9.2, that picture changes it becomes very different. You keep adding throughput as you add more concurrency up to the number of cores on the box. And the result, the difference in throughput is huge. I mean, actually, you can't see those numbers from the back of the room, so they blow that up for you. That is up here at the top, with 64 concurrent processes on 64 cores hammering away at Postgres, 350,000 queries per second. Woo-wee! NASCAR! About 75,000. So this is single-liner read queries. So this is the idealized case. Because the thing is, with single-liner read queries, it should be as fast as the processors can go. And now it is. So that's a lot faster. I can't really demo that on my laptop, so there's no demo for that. Now, of course, if all you were doing was reading, you wouldn't be using Postgres. So it's important for us to also improve write performance. So there were a few additional improvements in Postgres 9.2 to improve write performance. Improved group commit for transactions that are committing at the same time, so you could batch writes. Reducing some contention on the write-head log, reducing some checkpoint activity and that sort of thing. Again, works automatically. You don't actually have to understand what these individual features are. What you should understand is how it affects performance. So in this case, this was a smaller machine, 32 cores. Again, large memory though. And looking at hammering it with a write-only workload. And so this graph is from close to the end of development of 9.2 with some of the individual write optimizations that they put in there. And again, we can see, so this red line here is 9.1, and again we get up to about 35 concurrent write streams and it sort of levels off, whereas 9.2 pulls ahead and continues to scale up as your write concurrency scales up. And again, this results in, if you have a fast machine and if you have a huge concurrent write load, up to about 50% more throughput on writes. So faster on writes. Now, one of the other things that a lot of people do with Postgres is some data warehousing. Is anybody doing like analytics, business intelligence in Postgres? Yeah. So one of the things you do for business intelligence is you do a lot of bulk loading. So one of the things that we actually wanted to improve was to improve that bulk loading. And obviously on today's multi-core machines, the way you improve stuff is to sort of parallelize it. And people are looking, they'll say, hey, I need to bulk load 100 million records. And I divided them up into chunks of 10 million records and am loading them all simultaneously. And it's not really going any faster. There's some tools like PG bulk load that help you do that. And we looked at it, and the truth was, once you got up to about 3 concurrent bulk load streams, they would lock each other. And so anything over 3 would just get the performance of 3, or even a little bit lower. So in 9.2, we fixed that. You can now actually scale up to about 10 or 15 parallel streams, at least on the machines we were testing. Part of it depends on the number of cores you have, because often it's CPU bound. And that can result up to a 3 times increase in load speed for doing large bulk loading. So improvements in speed. So really the fastest Postgres ever. I was just talking to a user earlier tonight who's here somewhere who said, they just upgraded to Postgres 9.2 and they got thanks for the users. Wow, you really tuned that thing up. It's much faster now. They're like, yeah, we did a good job. So so you can do that too. Now, it's not all about performance. There's a lot of other features. Among other things, people really need a lot of availability and scalability and disaster recovery now. And so, actually, there's a performance feature where I can demonstrate. So we're going to talk about this a little bit and demonstrate it. Index-only scans. So this one thing was a little bit of an embarrassment to Postgres because other databases had it before we did. And we don't like that. We like to be first. And the idea of an index-only scan is this, is that here's our sort of abstract representation of, you've got a B-tree index on a text column and it's pointing to the heap. For those of you who might be familiar with other databases, in Postgres the table and any indexes are separate, they're separate files, they're maintained separately, that sort of thing. And so the heap, which is the table, is not in any particular order. And the various indexes sort of point to it. And one of the things that happens in Postgres, one of the things that we got a question from all the time from people who are coming from Oracle and MySQL was, hey, if I'm just looking for a text value that's already in the index, why do I need to go to the table at all? And the answer has to do with something called visibility, which is Postgres is a high concurrency system. And one of the things that can happen is, well, you're busy transversing this index in order to look up a set of values. Someone else can actually delete a couple of rows. And depending on when your request started, those rows are either visible to you or not. And in Postgres, that visibility information, as of 9.1, was contained only in the base table. So even if we didn't need to get any data from the base table, we needed to get the visibility information from the base table. And the reason this was a problem is that depending on what kind of search you were running, often the search on the index could be really fast, whereas checking the visibility in the base table could be really slow. So 9.2, we improved that, added index-only scan, and the way that it works, this is, by the way, the problem we called count star is slow in Postgres, which I'm sure people are familiar with. So in 9.2, we improved that, changed the way that it works. What happens in 9.2 is you look up and you transverse the index, and you find the values that you want in the index. But instead of looking at the base table, you look at this bitmap that's much, much smaller than the table, so it's usually cached in memory, called the visibility map. And the visibility map flags all of the data pages of the table that don't have any concurrency information, that are not invisible to any user. And therefore, everyone can see them, and therefore you don't need to check them. So in cases of a table that is not being concurrently heavily updated, we never have to look at the table at all. And then the result is that you get a much faster lookup. And that one I can demonstrate. So let's go ahead and do that. So I've set up a little PGBench database here. We have a table. So there's PGBench accounts. It's the largest table in your little PGBench benchmark database. And so we want to go ahead and, let's do something. So we're going to show you the old way of how it was done. So I'm going to turn off index-only scan. Except that's not what I want to do. We turn off index-only scan, and then we do a except that I want to show you how it executes. So I'm going to do a select count star from PGBench accounts, and because it's a moderate-sized one, and I'm on a laptop, takes a while, takes 3 seconds, and it's doing a sequential scan, which means a scan. So let's go ahead and enable index-only scan, and then we can do the same one, and that does an index-only scan on the table, which executes in about half the time. It would have been faster and it doesn't choose it, or when it wouldn't have been, where it isn't faster and it does choose it, please give us feedback on the mailing list because we need to tune that. But it's been pretty good so far. And the great thing about this is that, let's get a better, is that it works as long as the information is in the index at all. So it's not limited to doing things like count star or even direct value lookups. If you have, for example, an index on branch ID and balance, you can actually run a composite index. You can actually run a complex expression over those, and it will still use the index-only scan. So there I'm actually doing a summary of balances by branch across there, and it's using the index-only. And this executes in about half the time that it would have executed using a table scan. Now, the larger your the ideal case for index-only scan is table doesn't fit in memory, index does, and the information you want is in the index and you're only using part of it. And in that case, your speed up can be quite large, as in a fifth the time for the query, or even a tenth. In cases like here, where I'm summarizing everything in the table, it's about half. But it's still a nice speed up. So back to features. So now the other issue that you deal with databases a lot is availability. Needing to make sure that the database is available, maybe doing some load balancing, and particularly since everybody has servers in cloud hosting now. How many people are running Postgres in some kind of cloud hosting? Really? That's surprisingly few. Okay. I'm running a lot. Everybody's running stuff on cloud hosting now, which means you want to have multiple geos and that sort of thing. Now, in Postgres 9.0, we got binary replication. And binary replication was great because it was simple replication, it's high volume, it's high efficiency, relatively easy to manage, provides you a lot of availability. But 9.0.9.1, there's this tremendous limitation with binary replication where every single replica has to be connected directly to the master. Now, not only does that put load on the master, but it also puts load on the master's network interfaces. which can make a big deal if you're on something like cloud hosting where you don't actually get a lot of network bandwidth. So in 9.2, change that so that now you can have the master replicate to a replica and that replica replicate to other replicas. This is also lovely for taking binary backups because you can now take them from the replica instead of needing to take them from the master. But where it gets particularly important, I haven't changed this actually, I gave this presentation just in Australia and gave them an example of if the master is located in one part of the world and the replicas are located in a different part of the world, you're paying a lot of money for that bandwidth and you don't want to have multiple replication streams. So let's go ahead and demonstrate that. So if I haven't lost my internet connection, I got logged out, but you know. I've set up some cloud servers on GoGrid here. They've got a nice rubber stamping feature that makes it really easy to do this kind of demos. So I've set up a bunch of cloud servers. We've got the master and a replica master and then replica replicas. This one's actually messed up right now, so I'm not going to use it. So, see if I'm still logged into those. So here's the master. Go to the master. So the master is replicating to one replica. And then we've got, this is the replica master. And if you look at that, that master is replicating to one other replica. And the one other replica it's replicating to is this one right here, which is replica, right? Well, so what does it take to actually spin up a second replica? It's actually quite easy. And I said I would demonstrate PG base backup here. So we're here in a Postgres home directory here. You can't, actually, hold on. Can I scroll this up? Yeah, it's going to be a little better. So a little bit better for your people to see that, well, I don't know. Get that up to the top of the screen there. So that directory is empty, which is our data directory. So we want to go ahead and connect to the replica and clone it. So, so we're going to use PG base backup, and we need to connect to that 227. That's the replica master. So that's the first level replica. And I'm going to show you progress because it looks a little more interesting that way. And we want to make sure to copy all the transaction logs so we're in shape to bring it right back up. And then we're going to do it in the current directory. And so here it is copying. It'll take a couple of seconds to copy. And so what we're doing here is from the replica, we're taking a full snapshot of the database, plus its associated transaction logs so that we can spin it right up and start replication. And it's doing all of the, take a couple of seconds more. It's doing a copy right across there. As was discussed this morning, the purpose of PG base backup is to be a simple utility. It doesn't do much in the way of compression. It doesn't do any sort of differential file comparison or anything like that. If you have very large databases like terabytes in size and stuff, you're going to want to use something more like rsync. But for most people, PG base backup works great, particularly since it doesn't require installing or configuring any external tools. So there we're done copying. And so the first thing we need to do here is that we're going to need to, so right now, since I copied this from the replica, it's connecting to the master, which is .226. But I want to make this a cascading replica, so let's connect to the replica. And then let's bring it up. Oh, how about like specifying a directory? Okay, so there we've got it's up. And to actually see it replicating, let's take a look at the replica master. Actually, so that's the replica master, and this shows who its replicas are. And if you go to the master, you see it only has the one replica. So we're cascading down to 27, from 27 to 28 and 29. So cascading replicas, easy to set up. Easy to also get yourself in a world of hurt if you didn't think about how you configure your cascading replication setup. While they're fun, don't use cascading replicas just because you can. Use them because you have a legitimate reason, like you need to replicate between data centers and spaced out geos or whatever, or because you need to reduce the network load on the master. Because it does make managing a group of Postgres servers more complicated administratively, particularly when it comes to failover time. Oh, by the way, you can cascade them as much as you want. When we were testing this feature before it came out, trying to remember. Anyway, one of the developers set up a chain of 120 replicas. Took about 3 minutes for an update to get from the master to the final replica, but it did work. So back to features, cascading replication. But of course, we also added some other replication improvements. PG receive xlog, which is just reads from a replication stream, writes out to a file. A standby only backup, which is a side effect of cascading replication. Is anybody here using synchronous replication? Well, we added some finer grained control to synchronous replication in terms of how synchronous exactly has to be. So improvements in replication. But we also have some goodness for application developers in version 9.2. Number one of which is support for JSON as a data type with some other JSON features and that sort of thing. A lot of people are really excited about it. A lot of people were asking me about it last year when I was at Scale. And so it's in there. We still have a lot more JSON-related features we want to add and will be added in 9.3, etc. But what's there is already useful, and I personally am already using it in production. So let's go ahead and look at that. So first of all, one of the useful things, like we've got a couple of applications. One of our clients has, an application where most of the application is actually JavaScript. It's client-side JavaScript executing for that sort of thing. And the way they had it originally designed is the JavaScript calls out to mod Python application, which translates the JavaScript request, does a query to the database, gets rows back from the database, converts those to JSON, and forwards them out to JavaScript. And my boy, this relay through the Python server seems really unnecessary. Wouldn't it be nice if we could just query the database from the JavaScript and get back JSON as a result set? Well, now in 9.2, you can. One of the examples, simple. So we added some built-in functions, in C to actually convert, sort of Postgres internal tabular data into JSON. One of the simplest ones here is row to JSON, which takes a row and converts into a simple flat JSON structure. So libdata is an example public library database that I designed for training and that sort of thing. And so we've got this table full of book information. And you can do a row to JSON here, and then you have your simple JSON, sort of strings with a key value set that are what all of those columns were. So to show you in columnar format. So, it's like this in columnar format and that sort of thing. But that JSON is a lot more like what, this is what JavaScript would far rather get back. And just with that feature alone, we were able to take that particular application and eliminate the relay through mod Python in order to query the data. And it basically cut the number of servers that we needed to run that application in about half. Because we were able to eliminate a whole layer of fairly inefficient servers. But one of the things we say is, okay, so it's great you can get stuff back as JSON, but I also want to store JSON. I've got a whole bunch of JSON documents. So let's get a hypothetical. Imagine that we live in an enlightened world where public libraries actually keep their records about books in some sort of independent published standard like JSON. You don't want to see the formats that they do use. But imagine that we can actually receive updates to our public library database of books in JSON format. And we say, well, if I'm going to be querying that in JSON and doing a lot of manipulation in JSON, I want to store the JSON. So can I do that? And the answer is yes. So we added a JSON data type that's now its own independent type. and it validates that what you're putting in is correctly formatted to be JSON. And in the future, we're going to be building a lot of sort of features on top of that JSON type, like special indexing and that sort of thing. But for now, you can actually store stuff. So, and you just look at that, and again, we have that simplified JSON string, mostly because I just generated this out of the books thing. But it'll store any kind of arbitrary, you want to store nested structures, whatever you want, you can go ahead and use that. There's a lot of other stuff you can do using Postgres thing. We have a native key value type called hstore and some stuff for converting back and forth from JSON to hstore, or converting from Postgres arrays to JSON and back that help you manipulate it. But there's also something else that you can do, which is anytime that we have a really fast car, which is Postgres, we want some really fast engines to go in it. And in this particular case, the JSON type, our engine is PLV8. So we took, or we actually, Hitoshi, took Google's V8 JavaScript engine, just-in-time compiled JavaScript engine. And Postgres allows you to plug in almost anything you want as a procedural language. So you plugged it into Postgres as a procedural language, created PLV8, and all of a sudden you have a very fast executing JavaScript engine that can manipulate those JSON values that you're storing in Postgres in the first place. Here's your sort of usual example. People these days, when they're giving you an example of a new programming language, they always do a Fibonacci, with a sequence or whatever. But if you're just going to do Fibonacci sequences, you don't need to do it in Postgres. So let's actually do something you do need to do in Postgres. So say, for example, I've gone ahead and I've stored everything in this bibrec table. But then I say, okay, well, I really want to look up authors all the time out of this JSON value. Let's assume it was a complex JSON value where just flattening it into a table wasn't a simple thing to do. So I want to look up authors all the time. And I don't want to do it by scanning the whole table because it's really slow. I've read 1 million books in there. It would be really, really slow. So I want to create like an index on author. Can I do that? Well, with PLV8 you can. So first what we would do here is, we would actually look up the function we're looking up. So we create a JavaScript function in PLV8, which is very simple, which is that it makes the assumption that we're only looking up a single value rather than a JSON structure, and it goes ahead and pulls that JSON structure by key out of the value by key out of the JSON value and removes the quotes and returns it to you. Pretty basic. So once you've created a function in Postgres, once you've created anything as an immutable function, you can create an index on it. So I can do, let's see. There we go. I can go ahead and create a value, an expression index on there, where I say, okay, we're going to create this index called bibrec author, which looks up the author field of the JSON bibrec on there. And then if you actually do that, and we decide we want to look up an author, Postgres will use an index scan for that. It just works. For anybody here use CouchDB? This is a lot like CouchDB's indexes. You can do a lot of sort of the same things for that. So a lot of fun. You can obviously, anything you do in JavaScript, you can end up doing in V8 if you decide you want to use that as your general stored procedure language. But where it really shines is when you're manipulating JSON values. Anybody here use CoffeeScript? No CoffeeScript developers. It was just once Satoshi did JavaScript, it was easy enough to port CoffeeScript to Postgres. I understand CoffeeScript is fairly popular. I don't use it myself, but it's in there. Okay, so speaking of indexing, one of the things that the Postgres project has is a history of exotic specialty indexes, of all kinds of indexes for indexing special kinds of data or indexing data in unusual ways for high performance. In 7.1, we got the generalized search tree implemented by our mad geniuses at Moscow University. They seem to produce indexing geniuses at Moscow University at a truly frightening rate. And this generalized search tree, which was a generalizable sort of structure for indexing different kinds of data if you wrote a particular index for it, became the foundation of our geographic indexes and some other kinds of specialty indexes, our original full text search, etc. And that was great. And then 8.1, we got the generalized inverted index. This is an inverted index a lot like if you've used Apache's Lucene or its descendant Solr or Elasticsearch. Those are inverted index-based. We've got them in Postgres. That became the new foundation for full text search. It's also a great way to index arrays or genomes or other things that get broken into a bunch of discrete elements. So that was really cool. And in 9.1, we got k-nearest neighbor indexing, which is to index for proximity. Primarily, the main use for this is obviously geographic indexes, although actually the first implementation we got was actually indexing for similarity of text strings. Show me the 5 most similar text strings to this one using trigram. So that's really cool. And you would assume, given this history, that we'd be waiting until 10.1 to get our next new exotic index, right? Wrong. In 9.2, we have SpaceGist. So, SpaceGist is, it's a lot of, I am not an indexing genius, so it's a lot of sort of advanced indexing theory about how you construct indexes. Again, it's more of an indexing framework, so you build other kinds of indexes on top of it. So like, one of the things they've worked on is creating quad tree indexes to support geographic applications. So you can expect in PostGS 2.1 or 2.2 that you'll be seeing SpaceGist support in order to support better and bigger indexes. The main thing important about this is for a lot of stuff, like the geographic stuff where we've been using gist, you can get indexes that are both faster to update and faster to read. Here's an example, actually, from Theodore, one of the indexing gurus here, of creating a new index in regular gist versus SpaceGist. And so this is over a geographic information. And it creates in about half the time. The indexes are the same size, but they're faster. And for some of the stuff they're working on, like indexing things like URLs, where the SpaceGist algorithm can really actually make your indexes a lot smaller as well. So, other features. Now, one of my favorite features in here, because I have written multiple calendaring applications, and one of the things that I think is going to change more people's lives as application developers than they expect, are range types. The idea is that there's an awful lot of values in the world where the actual value is a range. Pretty much any time period is a range, right? This talk is from 1:30 p.m. to 2:30 p.m. It's actually 1:30 p.m. closed interval to 2:30 p.m. open interval in mathematical notation, because I'm actually supposed to stop a moment before 2:30 p.m., although we'll see if I do. But the range types that are now built into Postgres actually can index anything that can be expressed as a linear range between values, so including numerics and integers and other things. So if you had some reason why you needed to do computations over a line, you could express those line things as ranges. But the biggest use for it is for temporal values. So to give you an example of that, back to our library database, we have a history file, a history table, which contains a history of where every copy of every book was at given times back to when it was acquired. This has the copy ID, what its status was, that were things like checked out or on shelf or in transit or whatever, and a period of time. This is timestamp TZ range. By the way, everybody is using timestamp with time zone, right? I certainly hope so. Anyway, timestamp TZ range, which is the range of time that it was there. And if you actually look at this, it looks something like this right here. Copy 2952 in transit from 8/18/2011 to 8/23/2011 was busy being transferred between libraries. And it's there. So what is this used for? Well, one of the things that I can actually do here is I can say I want to see where every book was on May 1st, 2010. And so then you've got this, actually here, hold on. Let me bring that up to the top again. So there we go, on May 1st, 2010. So then you've got this little operator which says if the period was contained this timestamp. And so you go ahead and, oops. Oh, right, I'm using that. Hold on, wrong query. There we go. So I have to tell it that it's a timestamp TZ. So it contained that timestamp. And then we get a list of everything, where everything was, even if it began before that period and ended after that period. We'll find out where it was on that date. But you say, okay, well that's kind of cool, but I could have done that with between. You know, that works fine with between. What I really want to see is some of the calendaring operations like show me everything that overlaps with something else, that if we're using between and a starts timestamp and an ends timestamp becomes a real pain in the ass. Has anybody tried to do that, right? Where X is before this, or it's after that, or it's around this, or it's in between this other thing. I mean, those queries are really ugly, and they optimize very poorly. So let's do a little bit better, and we say, okay, so this says, give me every event in the copy history where the period of that event overlapped in any way with May 2010. And that works great. As a matter of fact, if you've actually created a gist index, that's even an indexed query. And this will tell you, you know, even if something was checked in 20 minutes into May 2010, it'll show up here, right? So this works great. Now, that's not the only thing you can do. We're a database. We're big on cleanliness of data and that sort of thing. So we say, hey, you know, what I also want to do is I want to make sure this is copy history. A copy can't be two different places at the same time. And so I want to ensure that by creating a constraint that says the copy can't be two different places at the same time. So let's go ahead and create that constraint. Now the syntax to do this, hold on. Okay. Sorry, I just didn't realize it was going to be so close down to the floor. The syntax to do this is a little bit obscure. This is basically saying exclude or actually raise an error for every value where the copy ID is equal and the period overlaps. So I'm going to go ahead and create that constraint there, and oh, what do you know? I should have had this constraint in the first place because it turns out in my data I do have two different books in the same place at the same time. So I'm going to need to clean that up before I can create the constraint and make sure that that kind of bad data doesn't get into the database in the first place. But Postgres now lets you do that. So, other fun stuff. Now, one of the things that any race car driver will tell you is that, what? Yes. Is that, you know, when you're looking for public domain race car pictures, you can't necessarily be picky. One thing that any race car driver will tell you is that races are often won based not on how fast you drove, but how little time you spent in the pit stop. And you know, and a good pit crew really can make or break a driver. So one of the biggest things about running, say, a public web service is not necessarily, again, what kind of level of throughput or efficiency you're getting on the service, but how little downtime you have. And in Postgres, we're all about helping you avoid downtime. And so there's a bunch of features that were added to Postgres 9.2. We've been gradually improving these things in order to allow you to deploy changes to the database without taking the database down. We add a few more of these every time. Postgres 9.2 is no exception. So for example, drop index concurrently. That allows you to sort of opportunistically drop an index when we can release all of the locks on that index without needing to keep trying and trying again until the locks are done. You can add a constraint that's marked as invalid at first so that you don't have to scan the table, do a full scan of the table during production time. Some more of the alter table statements do less rewriting of your table. We're trying to eliminate all of the cases where we don't really need to rewrite the table. Alter if exists so that if a page is locked by something writing or whatever, auto vacuum won't just wait forever for it to become unlocked. Yeah? When you set it valid, it does have to check the table. Yeah. But it's checked for new rows. So it allows you to do a deployment during the day and then actually check it during a downtime. Now, I don't have demos for that, but I do have some demos of this, which is the other really important thing for our high-speed race car database here is instrumentation, which is getting good knowledge of what your database is doing and how it's doing it so that you can make it as fast as possible and hopefully not get into an accident. So, one of my favorites, we've added some new stuff, and I'm going to demo the new PGStat statements, but we're logging for auto vacuum, tracking now of I/O information in Postgres, which is something people have been asking for a long time, some counting of deadlocks and that sort of thing, some checkpoint timing information, but the really fun one, is PGStat statements in my perspective. So, how many people here have used a tool like pgfooine or pgbadger to process the logs in your database and see what queries it was running, etc.? Okay. There's a couple of tools. People don't know there's a couple of tools where you can have Postgres log all of its queries, and then you run the log through the tool, and it provides you a really nice report of you ran this many of this kind of queries and all of these other things. And those tools do still provide you a lot of information, but they have a major problem, which is that you're saving up the logs for a day, and then you're running several gigabytes of logs through this external tool, and so the information you're getting is always kind of old. And in a lot of cases, you want to do things like you want to say, okay, I want to deploy this change, and I want to immediately see how it affected what's running on the database. And so that's what PGStat statements is for. It's an extension, so you have to install it. But once you've installed it, it automatically starts, giving you information about what has been running in your database and what queries have been running up to the limit of its buffer. So we've got this, where we're looking at, these are queries have been running or whatever, that sort of thing. Well, that's not very interesting. That was only run once. So let's actually, let's see what's using up the most time. So I ran a, oops. Sorry, wrapping problems. So if you do that, then you can actually get, the thing that used up most of the time, and this is because the PGEvents benchmark, was this update statement. And that ran about, so that touched about 250,000 rows. It hit a lot of stuff that was already in shared memory. So this is the I/O information. It hit a lot of stuff that was already in shared memory. But it hit a certain amount of stuff that had to be read off of the file system cache, possibly off of the file system. Postgres doesn't actually know. It dirtied a lot of blocks, and it had to write out a bunch of blocks. And you can actually sort of do calculations on those to figure out how this is affecting the performance and resources of your system overall. And so this way, while it doesn't have as rich information as you can get from the logs, it is instantly available, which the logs are not. And I'm really excited about it because we're using a lot of clients and that sort of thing. Now, one of the other things that we've added some small improvements to is explain. So explain, analyze now has some other options. You can report the number of rows that were discarded. You can set this no timing option, which is useful for a couple of reasons. One is often if the query is doing something like a nested loop, where it's repeating something every couple of microseconds, the recording timings can really affect the length of time it takes to run the explain, which then gives you deceptive results. So you can look at it with timing turned on and off. Also, for anybody who's using Postgres in Windows, is anybody using Postgres in Windows? Yeah, fortunately, there's a Linux conference. But for the poor benighted fools who have to run Postgres on Windows, the Postgres system clock is really slow. So for anybody using Postgres in Windows, you're going to want to switch the no timing option on a lot. Now, one of the things that I'm getting the most use out of, though, is having the I/O information in there. if you turn on, so explain, you can turn on various counters. If you turn on this buffers counter, you get some I/O information about what the query was doing. So we're going to do a table scan on the largest table in this database, and then it's going to tell me, actually, so you'll see a big difference between the two executions. So the first time I execute this, it tells me, hey, I had to read 166,000 buffers, 8K buffers, out of the file system cache that were not available in Postgres' dedicated cache. And therefore, if this was a real query that we can analyze, hey, why was this so slow? We know why it's so slow. It was reading stuff out of the file system cache or off of the file system. And if we actually execute it a second time, you can see the difference with cached information, because now, well, actually, Postgres has been set up with very few dedicated buffers. So we got, because Postgres had small buffers, we got a few hits on the regular buffer, but still to read most of the data. So more information for tuning your queries and for understanding why things are going on and why things are slow. Yeah? No, that means like if your rows were discarded because they didn't comply with the query.
Okay, regardless of the
Yeah, which can be really important, because imagine that it's actually doing a scan and only 1,000 rows comply with the query, and it's discarding 500,000 rows. The process of ignoring those 500,000 rows can actually be where most of your time is going. Yeah, because it's got to see that it doesn't. If you don't have an appropriate index, it has to check the actual row to see whether or not the row meets your filter conditions. So, some other features. Some folks put some work into lowering Postgres' power consumption, which is really important for somebody who's running a lot of servers, particularly our various cloud hosts. They're now offering Postgres as a service. More SE, PostgreSQL, SE Linux security stuff. Some improvements in the optimizer, as always. Some improvements in making Postgres PGHBA.conf more readable and having less weird gotchas. There were some improvements in the XML features. I don't know what they are. I don't use XML. But they added some stuff for the Postgres' built-in XML type. Exportable snapshots, which is something for the cluster developers and that sort of thing. So, some extra options for PG dump, PG restore, in terms of particularly dumping only specific parts of your database, like dumping everything except don't dump the triggers. Don't dump the triggers and constraints, which can be useful in a lot of circumstances. More stuff for PSQL, Postgres command line interface, because all of us developers use the command line interface, so we keep adding things to it. It's like an operating system almost now. We basically made the Emacs of database command line interfaces. More PG upgrade fixes and improvements and that sort of thing. And Bruce's old BSDI machine finally died, so we stopped supporting it. So if any of you were actually running Postgres in BSDI or like Ultrix, anybody running Postgres in Ultrix? Maybe running Ultrix period. You're no longer supported. You're on your own. So those are gone. And then that's the finish. Yay! Postgres 9.2 came out in September. We were very excited about it. We got a lot of good press. People were very happy to use it and very happy to upgrade to it, and have gotten a lot better performance. But, you know, I work on developing Postgres, so of course, by the time 9.2 came out, we're already thinking about 9.3. So let's talk. I'll mention in the few minutes that we have left, I'll talk about some of the stuff that's coming in 9.3 that we think is coming in 9.3. Keep in mind that 9.3 is still under development right now, and some features might make it or not make it. But some of the stuff is already in. More JSON goodness. New built-in C language functions for accessing JSON values and fragments of JSON and constructing JSON values, etc. To have that built into Postgres, so it's more useful as a full-fledged data type. Writable foreign data wrappers. If anybody's using a foreign data wrapper to interface Postgres with something like Redis or Oracle or MySQL or some other external database, it will be possible to write drivers that allow you to write data as well as reading it, because right now those foreign data wrappers are read-only. So they now be read-write, making them more of sort of a full-fledged solution. Event triggers. The basic concept is write a trigger on anything. Not everything is supported yet, but the idea is to be able to write triggers on, say, things like, say, every time this particular database user logs in, fire this event, which can be really useful for all kinds of management things that aren't covered by a trigger on a table. Um, automatically updatable views. If you have a view that's simple enough to be automatically updatable, then it will be. Create your own background workers. So if you actually are a programmer and you want to create your own sort of job scheduling worker to plug into Postgres and to automatically start up when Postgres starts up and shut down when Postgres shuts down, you can now do it. Lateral joins, a sophisticated SQL feature that allows you to use output from one table mentioned in the join list in another table mentioned in the join list. And you know, it allows really good SQL writers to shorten queries that were inordinately complex before, and it allows the rest of us to really mess things up. So, streaming only remastering. Currently, you actually have to archive transaction logs if you want to elect a new master, and we're finally eliminating that requirement. And improved foreign key locking. PGStat plans under development as a plugin in order to complement PGStat statements, so you can look at the query plans of your most common queries. And then the biggest one for a lot of people is, for people running Postgres, how many people here have gone into syscontrol.conf in Linux and had to change schmacks and small, right? Don't you love doing that? Isn't that a lot of fun? Yeah, well, it's going away. We've changed. We now only use a small amount of System 5 memory. The rest of it is map, and that small amount is covered by every operating system that we know of, and so you will no longer be changing those system parameters at Postgres install time. So, I don't know what time is it. Should have a couple of minutes left for questions. How are we doing for time? What? 7 minutes. So we have 7 minutes for questions. So go ahead. Yes. Like I said, out of the box in 9.3, I don't think every potential DDL operation is going to be covered, but a bunch of them will be. That's the main reason to have them, honestly. There is a chance. And it is something that you could affect, because they are currently being sort of debugged and debated on the hackers list. So if you are keenly interested in that feature, I would say download the patch and try it out and provide feedback that the feature is really important to you, because it's sort of on the edge right now. It could potentially. Nobody has implemented CIDR range yet, but it could be implemented. And it could be implemented as an extension. It wouldn't even have to be built in. So it's not currently implemented, but it could be. And that would be like a couple hours for somebody who has some experience hacking Postgres. Yeah, so you have, well, you'd end up rewrite, because it's stored as a single varlena, so you would end up updating the whole value anyway. But there are built-in functions to get the start point of the range and the end point of the range. So you could say, update this range to new start point plus end point of the old value. And that would work. By the way, range types also support the concept of infinity. So you can have an endpoint that's undefined on either end or on both ends. And of course, infinity overlaps everything. And that's a good value if you want to say, hey, this is going to cover everything. Then you give it infinity. In the case of data types that don't support infinity as a value, those are expressed as nulls. So it's important to know in the range types that when you see null, it really means infinity. Or negative infinity, depending. Not that we've been able to figure out. If you have the answer with that and can back it up with somebody's mathematical paper, then please post it. We had a custom sort of jQuery thing that actually did call that we had to add to the stuff. Well, not open, not publicly. That was custom code, in other words. Well, you wouldn't generally use them for the same things. I don't know that. I mean, I don't know that I've seen them compared on doing the same sort of things. Like, because with PLPGSQL, you're generally like doing triggers and comparing various data things. And for PLV8, you would generally be manipulating JSON values, maybe producing snippets of HTML, whatever. It would be interesting to try that, but nobody has. PLPGSQL, by the way, in general, it's not known for speed. So I wouldn't be surprised if even for data manipulation, PLV8 was actually faster, even though the code would be a lot more awkward. No, it should work. I believe it's completely Postgres specific. There was no standard for range types.
Yeah, I mean, I actually looked at that 10 years ago. I guess there are competing
Yeah.
range things and then five.
Yeah. The notation that we use is standard mathematical notation. But it's not like a published standard. And it's just not anything the SQL committee ever thought about.
No, they did actually. They weren't able to come to
Oh, they weren't able to come to a decision, yes. Well, that's not too uncommon with the SQL committee, so. More questions? What, in the JavaScript thing? Yeah. Well, we didn't, actually. It's an in-house application. So, yeah. No, you don't have to rewrite it. I can take what I've used and just put it back into a query. No, I don't think so. Oh yeah, but you can do this and it works perfectly fine. Oh, except I need single quotes here. The thing is that either of those formats works. Yeah, so they both work. So I can quote this. I mean, the thing is, what happens is I end up, depending on the values, I may end up having to use the double quotes because, for example, if I'm doing a full timestamp, then I've got a space in the middle of that. And particularly, if you were doing a value like if somebody actually implemented range for currency and you were European, you would actually be using a comma to indicate the decimal place, in which case we need to distinguish between that comma and the comma that indicates the two halves of the range. Yeah, so this means closed, and what closed means is it includes this endpoint. And this means open, and what open means is in a mathematical sense is it does not include this endpoint. Yeah. Yeah, and there's a bunch of built-in constructors. So like if you use the thing for TSTZ range and you just hand it a pair of timestamps and you don't tell it closed or open, it defaults to closed open. But you can always specify if you're going to have something that's different from closed open. Closed open is common for, say, calendaring, because that's how things generally go, right? It starts right at 1 o'clock, and it ends the moment before 2 o'clock, which is what, this says it starts right on January 1st and ends, 1 millisecond before March 1st. Other questions? Yeah. It's been talked about. Nobody has done any serious code implementation. There's a lot of reasons why that would be a nice thing to have, but somebody needs to spend a bunch of time. It's not an easy thing to do. So somebody would have to spend a season working on it. I don't think anybody seriously talked about that, actually. Partly because we haven't implemented things like streaming that have a broader utility than compression. The problem with compression is it's always a trade-off between CPU time and bandwidth, and that's often a bad trade-off. So only a few people would use compression. A lot of people would use streaming if we had it. Anything more? Okay, well, thank you very much, and go out and give 9.2 a try.